Hello everyone, this is Guido Giorgi, Beamline Instrumentation Business Development Manager. I would like to present you a laminography instrumentation we delivered to the ID19 Beamline at the European Synchrotron Radiation Facility in Grenoble. This project involved several institutes in France and Germany, the ESRF, the Fraunhofer Institute, ANKA, the KIT and the University of Karlsruhe. The synchrotron radiation computed laminography is similar to the well-known microtomography but adds a tilt degree of freedom to the axis of the sample rotation stage. This allows to analyze flat and wide samples. This technique is suitable for a variety of applications, including microsystem technology, materials science, paleontology, art, history, and life sciences. This picture shows an overview of the instrumentation we delivered in 2006 and we upgraded in 2010. This custom-made mechanics handles the scanning of the sample as well as the positioning of the detector heads. It was designed to be accurate and user-friendly in order to be flexible and easy to run. The technical solution we delivered can be easily described in the following blocks that I will later show you one by one: an elevation base, a granite structure, a detector stage with detector heads, a parallel kinematic Spacefab robot, a laminography rotation stage. At the base, we have a vertical positioning stage that holds the entire instrumentation. As you have probably noticed from the previous picture, the precision mechanics is mainly made of granite and steel. Therefore, this vertical lift must be strong and has to guarantee excellent stability over time. The user can translate the complete instrument vertically along a stroke of 200 mm, and he can also carry it around the hatch by pushing it softly from the sides. Let's have a look to the technology now. The floor of this hatch is polished, and the base is sitting on 3 feet, each made of a couple of air pads and which can operate in two ways: as a stiff anchor to the floor when off, or as no contact air bearing when inflated with pressure air. When the instrument is floating on air, the operator can carefully push it effortless no matter the mass of 2.5 tons. The lever system compensates the poor floor flatness. In the center of the stage we have a DC motor with tacho generator. A chain of motor shafts and self-locking gearboxes bring the rotation to every corner, where lead screws lift up symmetrically the load. An absolute encoder provides the position feedback. The stage is manually controlled with a joystick, and the position is displayed on a screen integrated in the controller box. The granite structure holds the micro-positioning systems on top and is provided with the alignment degrees of freedom that perfectly match the detector block with the sample block. This is a manual tuning done by lifting each block on air pads and by precisely adjusting the position with micrometer screw drives. Let's have a closer look. We have a base with 2 blocks sitting on top. Here you can see a bracket with a slot that limits the stroke for safety reasons and the micrometer screw for the adjustment. This is the air pad. A pivot point links the 2 blocks and a micrometer screw adjusts the angle. Here on the left you see a flexure bracket used to fix the position once aligned. When the air pads are off, the 3 blocks are locked in position by their weights, and they are solid just like one piece. The detector positioning stage is a particularly challenging XYZ motorized system because of the combination of off-axis high load, long stroke and high precision. In this context, I would like to put in evidence the straightness, flatness, and angular errors, which are extremely good. This mechanics has a simple design, and I'll show you some details that makes it so accurate. We have stepper motors in all axes. The long stroke stage is mounted directly on the granite and slides on needle bearings. In the center, we integrated a roller thread screw and an optical linear encoder. The transverse and vertical stages are mounted upside down. The carrier is still while the body is sliding in order to move the load off axis. The vertical stage integrates an harmonic drive gear without play. The lower part of the sample positioning system is a Spacefab, an extremely stiff parallel kinematic robot with 6 degrees of freedom. The pivot point and the 6 space coordinates can be freely set just as simple software parameters, and the controller takes care of the inverse kinematic translation. This animation shows some of the alignment and scanning functions easily performed with this solution. As you can see from the specifications, the Spacefab combines high load capacity with great linear as well as angular resolution. This is confirmed by these measurements. How do we get to this result? The Spacefab has a symmetric design with the moving platform standing on 3 legs and each one of these sitting on an XY translation stage. Above we have cylindrical joints and below we have spherical joints instead. The upper stage is an improved LS180 stage that mounts a 3-phase motor with resolver. The lower stage is mounted directly on the granite and slides on needle bearings. In the center, we integrated an optical linear encoder. The 3-phase motor actuates a roller thread screw. This flexible robot holds and moves the core part of the instrument, which is the rotation stage. The laminography technique requires that the X-ray beam goes through it, and for this reason, the rotation stage needs to be hollow, thin, and also tiltable to bend the rotation axis. These constraints make accuracy an even more difficult challenge. At a first glance, the specifications of the rotation stage might seem not exceptional, but considering the context just described, they are. We can deliver stages from the standard component catalog with eccentricity better than 100 nanometer, but none of those have a comparable shape or can be tilted from the vertical axis. I'll show you now how it works. The stage is made of steel, and below the rotating platform there are a precision air bearing and an encoder disc. The motion transmission relies on a belt with symmetric design to protect the eccentricity. A DC motor actuates the rotation. The tilt stage has precision bearings, and if we look underneath the stage, we can see the 3-phase motor and the rack and pinion system with self-locking gear on top. We described how to do accurate positioning, but not yet how to handle the sample, which is usually the most tricky part of the job. The sample holder must be fixed on a no-contact rotating platform and has to be thin and open frame. Very important is the alignment process. This animation shows the principle of operations. 2 perpendicular actuators place the square frame in the desired position on the rotation stage and then go back out of the rotating surface to avoid any interference. A very important specification is the position stability of the sample holder. Now some details on the technology behind. A square frame with magnets and Teflon pads on the lower corners lays firmly on the steel rotation stage. Two VT80 linear stages push it and pull it over a 200 by 200 mm stroke. The fingers touching the frame integrate air bearing and a magnetic preload that can be activated by an array of magnets. A standard micropusher MP20 switches on and off the preload by sliding the magnets with a custom-made sliding stage. A flexure bearing guarantees the parallelism of the sliding surfaces for a good performance of the air bearing. I end this presentation with this picture of the complete instrument. This is an example of how we can mix several technologies, standard components with custom-made solutions, how we can define for customers and with customers the best process of positioning with the application in mind. To deliver such an instrumentation, we like to go deeply in discussion with our customers and clearly understand the use of it, like partners. Thank you so much for your attention.